Hey, good afternoon, everyone. How are y'all doing?
Hi.
Good, how are you?
Good. Thank you all for meeting me on Zoom instead of me having to go in today. I'm still trying to juggle the whole thing with my wife. She's doing good, so I appreciate I can kind of keep an eye on her being here. But Wednesday we will plan on being back on campus. For those of you who want to join, I'll also Zoom the class. So first thing I want to start with is I had you watch a video of me doing all these problems. Were there any questions over the ones that I asked you to turn in and upload for me? Did these go okay? There weren't any issues? So we're happy. We can move on then.
I think so. I had a little bit of a struggle with 69, but other than that, everything went fine.
Okay. We can work through it if you want. I have no problem with that. Okay, so we're asked to solve for X here. So do you want to tell me kind of what you did, and then I can kind of see if that's in line with the right approach?
Sure. Okay, so for 69, I took the 4 to the x power and I turned that into a 2 to the x power with but like squared.
There you go. Good. Yeah.
So that I could substitute the 2x with u.
Good. Okay, so what we're trying to do is turn it into a quadratic, right? That way it looks quadratic to us. So we replace 2 raised to the x with u. And then you have this quadratic should be 3u squared plus 4u plus 8 equals 0, right?
Yes.
Okay, what'd you do with that? Did you go to quadratic formula or does it factor?
Well, I was trying to factor it. I guess I didn't think about using the quadratic formula. That would probably be where I had a problem.
Yeah, let's see if it factors. So if we're looking for 2 numbers that multiply to be 24, 3 times 8, but they have to add up to be 4. 2 numbers that multiply to be this, but add to be this. And I don't think it's going to happen.
Yeah, I couldn't find one. That's why I was struggling with it.
Yeah, so we'll have to go to the quadratic formula here. So that means using the quadratic formula and realizing that our variable here is u, not x, we will have that our solutions to this will be negative b plus or minus the square root of b squared minus 4 times a times c all over 2a, where a, b, and c are the coefficients, a, b, c, right? So we're just going to plug these into the formula and see what we get. So negative b should be negative 4 plus or minus the square root of b squared. So we square our 4, we get 16 minus 4 times a times c. Over 2 times a, like that. I said do you all know why I said
The number inside the square root is going to be negative.
Yeah, what we're going to get under here is a negative number. And if that's a negative number, right, that's going to be, yeah, it's way negative. So that means that there's no solution. Okay, there's no solution to this, no real solution. There's a complex solution, but there's no real solution to this. And if there's no solution to that, then I can never replace 2 to the x in for u, because we're basically saying 2 to the x equals this thing, but there's no solution to that. So that means there's no solution to the original problem. That's kind of boring. That didn't work out the way. I think the one I did, number 70, I believe it did work, right? The one I did on video did work. So, but that's what happens if you get this to get your quadratic to have a negative under the root. We have no solution. We have to move on. Any others you want to look at? We're good? Okay, let's look at where we are here on our schedule. Let's see, where is it? Here we go. So today is the 15th, and we're supposed to do exponential growth and decay models. And let's see, exam-wise, we just had an exam, so we're not going to do this exam, right? We had moved it before the drop date, so we're not doing this. So we're pretty much going to grind out till the end here, right? Let me double check something here. Give me a second. What are we going to do here? What do y'all feel like doing? We have to figure out, are we going to try and cram a third exam in here? How do y'all feel? We've done 2, right? Because we have this week, we have all of next week, then there's Thanksgiving, but there's not a holiday for us. And then we come back and we have 1 week. That's it. So we only meet, what, 6 more times? Do we want one of those to be a test? What do y'all think? How do y'all feel? Let me tell you what, if we didn't do a test, then basically I would look at your exam grade, whatever you get on your final exam would take the place of that third exam, or the best exam score you have would replace that third exam score. So if it's the final that's your best, then it replaces exam 3. If exam 1 is your best, it replaces exam 3. Or would you all prefer to just put a test somewhere in here in the next 6 class meetings?
I would just take the best grade.
Do you all feel the same way?
Yeah, I agree.
I agree, yeah.
Okay. Anyone object? All right, let's go with that. Let's go with that for now. That we're just going to continue to crank through the material and see where we land. We'll be able to know by the end of next week, like how far we are. I'd like to get through all this material just because you're all going to go on to pre-cal, and there's some stuff in here I want to make sure you know how to do. So yeah, let's do that. Notes for today. So just like previous classes, the notes I'll send out later. Today is all word problems. Okay, so we're going to do applications of exponential and log, mostly exponential, solving exponential equations. We're going to do, where we can see these in the real world. So on your notes, the first 2 pages are your homework assignments. So do all of these problems. Number 2, 3, 10, 11, 13, and then there's a few more here, 23 and 27. So those are your word problems. See, they're all word problems here. So let's get started so we can see how to do all these. So we're talking about exponential growth and decay models. We're also going to talk about Newton's law. It's actually called Newton's law of cooling. And then there's something called the logistic growth and decay model. So there's kind of like three main topics here: exponential growth and decay, Newton's law of cooling, and logistic growth and decay. Those are the 3 main topics. And the first thing we're going to talk about is what's called the uninhibited growth or decay model. So this is a formula. It's a function, a of t equals a naught. This is a subscripted 0. We say a naught times e to the kt. And notice that e in there, that's the e we talked about, that very special number, e to the kt. This is a formula that models what we call uninhibited growth or decay. So I'd like to start by showing you a graph of this, of what a function like this would look like. So I'm going to put here, let's see, y equals a times exponential k times, I'm using some different variables here because the system I'm working with here. So the k here I can adjust, and the a is the number in front. So if I adjust the a, it changes the exponential growth. If I adjust the k, watch what happens. It gets steeper, and if I let k go negative, it flips over to exponential decay. So if k is positive, we have growth. If k is negative, we have decay. And then the a is just a stretch. It just stretches it vertically, or it could reflect it over the x-axis. So we've seen things like this in the past, like, reflections and stretching. We've seen that. We're going to be using that to model this thing called uninhibited growth. So just to identify what each piece of this function is, the a naught, this number out here, is always going to be the initial amount that we start with. So we're looking at things that grow or decay out. The number out front is going to be what we start with, the initial amount we call a naught. The k is what we call the growth or decay rate. That's this number up here. If that k is positive, we have growth. If that k is negative, we have decay. And then the t up there is usually a measurement of time. And you have to be careful with that because sometimes it can be measured in seconds or minutes or hours or days or months or years. So you have to read the problem and understand within the problem what they're measuring t to be. And then the left side of the equation is actually how much stuff we have after a certain amount of time has gone by. So that's our master equation that we're going to use anytime we're talking about uninhibited growth or decay. So with that formula, let's look at our first example. And this is an example of bacteria growth. And I remember when I was first telling you about exponential growth, we did an example in class where I was folding up paper and doing all that stuff. This is along the same lines as that, but now we have something that has been observed through like a scientific method. So someone has done some research. They're looking at this colony of bacteria, and they say that the colony is growing according to the law of uninhibited growth. So they're telling us, when they say this, they're telling us that the model for this is that a of t equals a naught e to the kt. They're telling us that it follows this model right here. Now, what they've done is, because they're talking about the number of bacteria, they've kind of revamped the formula. And instead of using a of t, they decided to use n of t, n standing for number of bacteria, as opposed to a, which stood for amount of something. And then the rest of it is provided, 100 e to the 0.045 t. They tell us here that the n is measured in grams. So they're measuring how much bacteria is there in grams. So they're weighing it. And then they're measuring the time is measured in days. All right. So we have, with that sentence, we have everything we need to answer the following questions. So the first question, A, is to determine the initial amount of bacteria. So who can tell me how much bacteria we started with?
100.
100, right? That's the number in front, right? We said that's the initial amount. That matches up with 100. So 100 what? Just 100 what? 100 bacteria?
Bacteria.
Or what's that?
100 grams.
100 grams, right? So that number, right, represents how much of the bacteria we have, and we're measuring that in grams. So the answer would be 100 grams of bacteria to start. Now, part B asks for the growth rate of the bacteria. So who wants to give me the growth rate?
0.045T.
Okay, yeah, so the growth rate is the K, right? It's the number in front of the T. And so we're gonna put 0.045, and that is it. We're gonna leave it as a number, okay? We're not gonna say it's like, that's not time or anything else. It's just the rate that we're growing. If you want to, it's not wrong. You could convert it to a percentage if you want to move the decimal point 2 places to the right. So you could say that it's, you know, its growth rate is 4.5% growth, right? Part C, what is the population after 5 days? So who wants to tell me what we need to do for part C? What is it that we have to do with this formula we have?
Substitute 5 into T.
Yep, that's it, right? We're just going to take the original function that they gave us, n. We're going to replace the T with 5. And so we're just going to go in here and we're going to replace that T with a 5 right there. Right? 5 goes in for T. And now we need our calculators, right? We need to be able to evaluate this. So we need to be able to plug everything in properly here. So what I'm going to do is on my calculator, I'm just going to first do 0.045 times 5. And that gives me 0.225. And then I'm going to use my E key and raise E to the 0.225. So I get 100 times, and then on my calculator, I'm getting 1.252322716. Multiply that times 100, and it moves the decimal point over 2 places. Now, they want to know the population after 5 days. This is the population. Are we saying 125 bacteria? What are we saying here?
Grams of bacteria.
Grams. So we want to put 125. We can round, let's just say 0.23 grams of bacteria. So it's grown, right? It's grown. At the very beginning, we had 100 grams, and now 5 days later, we have 125 grams. So it's grown. Now, one thing to be careful with when you're reading problems like this, what if they had said here, what is the population after 5? What if they said 5 weeks, right, instead of days? We would have to say, okay, wait a minute, hold on. The formula measures things in days, right? So for T, we wouldn't plug in 5. We do 7. We do 5 weeks, right? So we have to do 5 times 7. That'd be 35. So just be careful in the wording, because that's where students can get caught up sometimes, is they get ahead of themselves and they don't see that, you know, the formula says days, but this says weeks, and they don't do that conversion. So just pay attention to that. All right, how about part D? What are we doing for part D? This is where we finally get to do everything we've done up to this point is pretty basic. Part D actually requires some more advanced techniques to get a solution. So how do we do part D?
Do you put 140 on the other side of the equation and then solve?
That's right. So we want to know how long it's going to take, right? Which means we want to know the time. How much time does it take for us to have 140 grams? So we take our formula here and we want to know when is this 140? So we set the left side of the equation equal to 140, leave the right side of the equation like this. And then we need to go now solve for T. Okay, we need to figure out what that T is. And this is exactly what your homework was about last time, right? It was all about how do you solve equations when your variable is up in the exponent, right? How do we do it? How do we do it? So hopefully this is not too foreign to you when you look at it, right? We're going to first try and isolate the thing that's being raised. So I'll divide both sides by 100 first. This should give me 1.4 equals e to the 0.045 t. And then from your homework, how do we do this? If we've got that thing isolated, what do we do now? How did I do it?
Would that be the circle?
Yeah, we're gonna create the log from this, right? Because the thing we're trying to solve for is up here. So I'm gonna create a log thing here that the loop should basically get me this equation. So I'm gonna put log, what's the base of this log?
E?
E. And then equals over here. Now we need to think about the loop. The loop should match this equation. So we're taking E and we're raising it to the 0.045 t. And that must equal the 1.4. So we go from the exponential equation and we convert it to the log equation. And the good thing about the log equation is that now t is down, right? T is no longer up in the exponent, it's been moved down. And the left side of this equation, I hope you all recognize, log base e is the natural log. So I'll be able to use my calculator here to figure out the left side of this equation. So I'm doing natural log of 1.4. And this will be 0.33647. I'll just go there. Equals 0.045 t. And then the last step would be to divide both sides by 0.045. So divide that by, I get about 7.47 is roughly what t is. Double check that. Somewhere about 7.48, 7.47. So about 7.47 what? Grams? What is this?
Days.
Days, right? T is our measurement of days, right? Time. So it's going to take approximately 7.47 days for us to reach 140 grams. Questions there? The last question, what is the doubling time for the population? Doubling time, we haven't even mentioned what is doubling time? So doubling time, what they're asking us is, can we determine how long it takes for the population of this thing to double? So how long does it take? So how should we do this? How should we go about this? We have this master formula right here, right? We can use this formula any way we need to. And they're asking on part D, oh, sorry, E, they're asking for the doubling time, right? So we're trying to solve for time, right? But we want to know how much time it takes to double, which means what? What can I do here?
Put 200 on the left side of the equation.
Exactly. So we want to know how long it takes to double. We know that the initial amount was 100, right? So if we know the initial amount was 100, we want to know how long it's going to take for it to become 200. So if we replace the left-hand side of the equation with 200, then we can go about the same procedure we just did on this problem over here. Instead of putting 140, we put 200, and let's just go through the same thing. Divide both sides by 100. Create the loop. take on the left side the natural log of 2. And then divide both sides by 0.045. And you should get 15.4 approximately days. It'll take 15.4 days to double. What if they had said, any questions there? What if they had asked us to find the tripling time, the time it takes to triple? How would we change the problem?
Will we just change the left side to 300?
Go to 300, right? If it said, how long would it take to quadruple, then we would replace it with 400, right? So it depends on the language of the problem. Here they want to know the doubling time. So we put twice the amount of the initial value, which is 100, we just doubled it. But we could just as easily have done triple or quadruple. Questions? That's our first example.
I have a question.
Yes.
Would it not, is there a reason it would not also work to just take the number of days from the first equation and just double that number or triple that number?
Let me see, the number of days from the first equation, I'm not
Sure.
sure.
What we
which
got
one.
with the 7.47 after we figured out the time in the first equation, if we were to just take that number and double it, would we, is there a reason that we can't do that to get what the doubling time is?
Double this amount to get
Yes.
that?
Yes.
Is that what you're saying? If I double this, I get this?
No, I'm just asking if there's like a reason why that would not work, like why that couldn't be the answer.
Okay. Because it's not linear, right? It's not linear growth, it's exponential growth. So I want to make sure I understand your question, because this 7.47 days came from us asking how long will it take to go from 100 to 140, right? So from 100 to 140, it took 7.47 days. This question is asking how long it takes to go from 100 to 200. Are you, see, I'm trying to see where you're seeing the connection.
Never mind. I didn't word that correctly. Never mind. Sorry.
So I'm going to answer your question because I think I know what you're getting at. You cannot, this brings up a bigger question is, maybe I can answer it this way, Carissa. This is how much time it took to double, right? Okay. What about quadruple? To be 4 times as much, right? 4 times as much? Instead of twice as much, 4 times as much. Do you think that would be just doubling this? Is that kind of what you're saying?
Yes, that's what I was asking.
Okay, so let's see. What do y'all think, everyone? To go from 100 to 200 to 15.4 days. How about to go from 100 to 400? Do you think that it would be twice as much as this? What do y'all think? Do you think it'll be 30.8 days?
I think it's
We
going
could-
to be bigger, or
I mean, we could do it real easily, right? We could just say, hey, what 400, right? Equals 100 e to the 0.045 t, right? That would be how long, we're asking how long does it take to quadruple, to become 4 times as much? So we divide both sides by 100, we get 4, right? 4 equals e to the 0.045 t. And then you take the log, well, we convert this to a log e4 equals 0.045 t. And then you do that on your calculator. Again, it's natural log, right? Because it's log base e. So you get 1.38629 equals 0.045 t. and then divide that by 0.045. And you get, 30.8 is approximately T, days, right? And Carissa, that is twice as much. That's twice as much time, isn't it?
Yes.
So it does look like, it took to go from 100. I think I'm going to draw it out for you because I think it'll make more sense. If this is time at 0, here's time. At 0, we were at 100, right? At 7 point, oh, no, not 7, at 15.4 days, we were at 200, right? So at 0, we're at 100. At 15.4 days, we're at 200. And then to get to 400 took another 15 days, 30.8. Like that, right? Go with me?
Yes, sir.
So this looks linear? No? Does it? Doesn't this kind of look linear? I mean, to me, that looks like a straight line. Right? This went over, you went up. You rose 100, you went over 15, right? Here you rose how much? Oh, wait a minute, hold on, this is not linear. What's wrong? This is 400. That's 300, isn't it? This is 400. Put my dot in the wrong place, sorry. Yeah, no, now you're not linear, right? Like this. So I have a question for everyone here. What would happen? What do y'all think is going to happen? Where would we be if we added 15.4 to this? So add another 15.4 to this. What would you get? What's that? 46.2? Where would we be?
Roughly 800 grams.
800?
800, right? So I just want to make sure you all understand, we're not going up by 200 each time. We're doubling each time. So this next time we go out that same amount of time, we're going to now be up here at 800. So Carissa, I don't know if this is what you were asking me, but there is a connection between the time, right? If we keep adding that much time, every time we add that increment of time, we keep doubling the population. Not multiplying by 2, right? We're doubling whatever was there before. So it went from 400 to 800, right? 800 is going to go to 1600, and the next time 3200, right? It's going to keep growing very fast. Carissa, have I just confused you, or have I clarified anything here?
That essentially answered my question. It was my mistake at the beginning when I asked it originally. It didn't ask the way I needed it to be asked.
Yeah, the thing was with the 7.47, that was a kind of a weird number. That's 140. So that wasn't quite like a double. And that's why I couldn't really say, yeah, 7.4. Okay, let's look at our next example. Read through this. We've got uninhibited growth of a bacteria. They have not given us a formula. Do you all see that? We do not have a formula. All they've said is that we have uninhibited growth. So part A says if n is the number of cells, right? Number of cells, not grams. And t is time in hours, not days. Express n as a function of t. So the very first thing that they want us to do is come up with the formula for the number of cells n as a function of time. So we want the number of cells as a function of time. Here's what we know. It follows this generic model. A of t equals a naught e to the kt. That's the generic formula for uninhibited growth. Here they want us to use n instead of a. So we know that this should be n of t equals n naught. I'm going to use n naught instead of a naught, then e to the kt. That is the answer to part A. It's just us saying, yes, we understand that we're going to have to use this model because it's uninhibited growth. Just replacing A with n's. What we don't know right now, okay, what we don't know is we don't know K and we don't know N naught. We don't have those two things. In the previous problem, we did, right? In the previous problem, they gave that to us. It's right there. They gave us all we needed and we answer the questions. Here, they don't. Not directly. They give it to us indirectly. So let's look at part B. If the number of bacteria doubles in 3 hours, find the function that gives the number of cells in the culture. Okay, if the number of bacteria doubles in 3 hours. Okay, how am I going to use this? The number of bacteria doubles in 3 hours. Find the function that gives the number of cells in the culture. So what part B is telling us is this: when t is 3, right? Right, they're telling us when 3 hours have gone by, the number of cells doubles, doesn't it? That's what they say. That's what they're saying. If the number of bacteria doubles in 3 hours, find the function. So we know that when t is 3, the number of cells should double. So what equation can I write down now? See if anyone gets this.
3n equals n, the initial n, e to the 3k.
I'm going to do k times 3, but yes, it's the same thing. Okay, very good. So let's see, we're replacing, all we're doing is replacing t with 3, right? We know that that t has to be 3. K is still, we don't know. And to say that the number of cells doubles, oh, sorry, is it doubles? Sorry, did you say 3 or did you say 2? I don't remember.
Oh yeah, it's either 3, but it's 2.
Yeah, it's 2. Okay, so we are plugging in, for t, we're plugging in 3. And then we don't know how many cells were there in the beginning, right? We have no idea how many. We just called it n naught, n sub 0. But when you plug 3 in, we should double that n naught, right? Whatever n naught was, we were going to double it. Now, it may appear to you right now that we have 2 variables we don't know. But let me ask you, can you solve for k right now? Could you? Could you get k? What would be your first step to get k?
Divide both sides by n.
Yeah, divide both sides by this and not just like this. See, it's kind of nice. We don't actually even need to know what that value is because it's going to cancel. We're going to get 2 equals e to the, and I'm going to write this as 3k now. And once I have this, I can convert this to a log. Use my little loop idea, right? The left side is natural log of 2. Oops. Which comes out to, we did this earlier, 0.6931. I'll just go, yeah, I'll go there. Equals 3k. And then divide by 3. You get approximately 0.23104, let's say, equals k. Questions on what we did for part B? We're not done with part B, but questions on what I've done so far. Taking the information that the bacteria doubles in 3 hours, we were able to use that, right? That information. And from that information, we were able to figure out what K is, right? Any questions on that? So that means we're trying to come up with the function that gives the number of cells. So the function, we already knew the function had to look like this, but now we know what k is. So n of t equals whatever the initial amount is, e to the k, which we just found to be 0.23104 t. This is now our formula, right? Y'all see that in this formula, we have now solved for k, but we still don't know how many are there in the beginning. We have no idea how many cells are there at the beginning. We just know that whatever it is, how much was there in the beginning, this is the actual growth rate for it. Can we answer part C now? How long will it take for this size of the colony to triple?
Yes.
Okay. So how? For part C, what am I going to do?
Replace
The left,
the,
yeah.
replace the left side with 3 times n naught.
3 n naught, triple, right? We want to know how long it takes to start at n naught and triple it. And then this side 0.23 e to the 0.23104 t. And just like before, we can divide both sides by n naught. And we're going to get a nice number on the left side. And then we can do our loop and go about solving again, right? So log base e of 3 equals 0.23104 t. Now I'm going to do the natural log of 3 on the left side. This is going to be 1.0986 equals 0.23104 t. I'll divide both sides by 0.23104. And I'm getting 4.755 is approximately t. And t here was measured, if I recall here, t was measured in hours. So this is going to be hours. Questions? Let's see what the last question is asking. How long will it take for the population to double a second time? That is to increase 4 times. What do y'all think? Can we do this without doing any work?
Can we just multiply the doubled value by 2?
Yes, and this is what Carissa was asking, I think, in the beginning, is that we know how long it took to double, right? The amount of time it took to double, right? Did they tell us? Did they tell us how long it took to double?
3 hours.
It took 3 hours to double, right? So if we wanted to double again, right? To increase 4 times. I'm going to draw a picture again to kind of illustrate what's happening. We know that at 0, the amount was n naught. We don't know what it was. We know after 3 hours, it doubled, right? And became 2 n naught. So it was here, and then after 3 hours, it doubled. And now we want to know how long it would take to double that again. So we want to know how long does it take for this to become 4 n naught. Well, that should be double this time, which is 6. 6 is how long it should take to get there. That's exponential, not linear. So 6 hours, right? Is what it should be. Now, what if we didn't do it that way? What if we just set up the equation? We would have, well, we want it to quadruple, right? 4 times the original amount equals n naught e to the 0.23104 t. we could go about the same thing and go through all the math. Cancel the end knots. I'm gonna go fast through this because I hope you would know how to do this. Create the log. It's gonna become natural log 4 equals 0.2314t. And then I'm gonna do natural log 4 on my calculator. I'm gonna get about 1.38629 equals 0.23104t. I divide by 0.23104, and I'm getting on my calculator 6.00023 is approximately t. So there's some rounding error here, because these numbers, when you do natural log of 4, we have to round. So we're not getting exactly 6 doing it this way, but we're saying it's approximately 6. If we just go off of what we know about, the doubling and how it works, then we can just double that answer 3 hours and get the same result. And how much would be there after 9 hours? So after 3 hours, we'd have twice as much. After 6 hours, we'd have 4 times as much. After 9 hours, we would have
8 and not.
8.
8 times as much, 8 and 9. And how about at 12 hours?
16 times as much.
16, right? So it's not going up by 2 each time, it's doubling the entire amount each time. All right, any questions on that? In your homework, problem 2 is basically this, all right? So see how that goes for you. I feel like I'm missing a problem here. Hold on. No. All right. I'm going to give you a moment to read through this. Okay. This is actually something we really do in the real world. This is the way we estimate the age of things that we find. Archaeologists use this. They use what's called carbon dating. And this is basically the idea right here. So let me give you a minute to read through that. And then we will see how much of this you can do. Let me give you like 3 or 4 minutes, just see how much of this you can do. I will tell you that with carbon dating, this is an example of uninhibited decay. So our formulas are going to look like this. Okay, it's like this, but it's decay. So this K that we get here, our growth rate should be a negative number. So take a minute or two just to read through the problem, see if you can't fill out any of this with what we're given. This might be a little tough. See what you can do. All right. So this problem is all about this concept called a half-life. All right. So I know some of you have heard of Half-Life before. I'm not talking about the video game, right? Isn't there a video game called Half-Life? It's not what I'm referring to here. The half-life of things has to do with this idea that Let me get a piece of paper here. That certain substances that we find out in the real world, they start to decay away. I like to think of it like the way I think of it is like a campfire. That's a fire. I know it's pretty impressive. Okay, when you're burning wood, okay, and this has nothing to do with the wood that's up here, okay? Just if you're burning, think about a campfire. You get it going, it's real hot, right? And you just let it burn and burn and burn. You come there the next day and you'll probably still have little smoldering, ashes in here. And if you stick your finger in there, it's probably still hot, right? And over time, it starts to get cooler and cooler and cooler. Imagine that fire never truly goes out. Okay, I know in the real world it does, but the half-life of something is how long it takes for half of it to go away, to decay away. So I think of it as like, how long does it take that fire to become half as hot as it was before? So for every substance, there's a different amount of time that it takes for half of it to go away. And then it'll take that same amount of time. So maybe that took, 2 hours. And then 2 hours later, another half goes away. And then maybe 2 hours later, another half. And 2 hours later, another half. And 2 hours later, another half. Right? And we keep doing this another half. I've done this before for y'all. The thing is, it never truly goes away because we can keep doing this forever and keep cutting in half theoretically, right? We'll still have something there. So this idea of a half-life is an example of uninhibited decay. And so we can use this formula. And the key here is that they're telling us about this thing called carbon-14. And they're telling us that the half-life is 5,730 years. So for carbon-14, it takes 5,730 years for half of it to go away. And then another 5,730 years later, another half goes away. And so when this thing carbon-14, it's present in all living things. Us humans, we have carbon-14 in us. Trees, plants, animals, they all have carbon-14. And your body in trees, they pretty much automatically replenish the carbon-14, always keep it at a certain level while you're alive. But as soon as you die, your body stops producing the carbon-14. So it starts to decay, but it only starts to decay as soon as you die, or as soon as a tree dies, or as soon as an animal dies. So what we can do is we can say, oh, okay, well, if there was 100% of the carbon-14 in the beginning, then when we find the bone or the tool or whatever it is, tree, if we look at it and we measure the amount of carbon-14, we can tell. It's like picking up one of these little pieces of paper and saying, oh, well, look, that paper came from a bigger piece of paper. And what I need to know is how long it took to cut it down to this size. And each time we cut it in half, it took 5,730 years. So it's kind of working backwards. We start from the small square and try and get back to how long it took to get it back to the big square. So carbon-14, half-life is 5,730 years. So here's the way I'm going to use this. First thing I'm going to do is this. I'm going to use this formula, but I'm going to use the idea that I know how much time it took, right? If T was 5,730 years, then we have half of however much we started with, which is A naught, right? We should have half of A naught, whatever A naught is, we should have half of it after that much time has gone on. So that means I can take this equation and I can write 1/2 A naught on the left side equals A naught e to the k times 5,730. See, this is kind of like the doubling time that we did in the previous problem, but it's like a halving time. So this is the amount of time it takes to go from the full amount to half of what it was. And then we just follow the same procedure that we did before and try and solve for k. Once we get k, we will know in this case, the decay constant, and then we will have the master formula. So I'm going to now go about solving for k. Are there any questions on how I'm using the half-life? Okay, divide both sides by a naught. Now I create the log. Base E, 1/2 equals 5730. K, this is the same as natural log of 0.5 equals 5730 K. And now you're going to get a very small number here on your calculator. Not on this step, but on the next step. So this is negative 0.693147 equals 5730 K. And now I divide by 5730. So I get negative 0.000120968 equals K. Now I'm going to use all the decimals on my calculator, because the more decimals I go, the more accurate I'm going to be. This right here is our growth rate, or in this case, our decay rate. So from here, I can actually come up with our formula. A of T, the amount of carbon-14 we have will always be the original amount, E to the negative 0.000120968 T. And now I have my master formula. Questions? I'm not done, right? I'm not even close to answering this problem. All I've done is use the fact that I know that they gave me the half-life of carbon-14. Once they give me the half-life of carbon-14, I can come up with the exponential model for the decay of this stuff. And that goes for any substance. If you are given a half-life of something, you can always generate the formula, and you'll always just use the solution or the method I just did right here. So now let's get to the question. Traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. If the half-life of carbon-14 is 5,730 years, approximately when was the tree cut and burned? So we have the formula, the master formula, and we found the decay rate. Now what we need to do is use this 1.67% somehow to determine how old this thing is. So the 1.67% is how much of the carbon-14 we have when we found the bone, right? So what I can do is I can say on this equation, the amount that I have when I found the bone is 1.67%. I'm going to convert that over to a decimal. That's 1.67% converted to a decimal. This should be equal to, well, how much carbon-14 was there at the very beginning? This is a key to the problem right here. How much was there in the beginning? It's right when the thing died, right? What percent of your carbon-14 should you have?
100%?
100%. 100%, right? But we need to convert that to a decimal. So A naught should be what? 1, right? 1 E to the negative 0.0001200968 T. So this is key. I mean, I hope this is where you ask questions, okay? 1.67% is the way we found the bone. This right here represents the 100% because we said when something is alive, it has all of its carbon-14. So in the initial time here, when T is 0, right, that's when the thing dies, it should have 100%, and then everything starts going down after that. If we have that equation, we can solve for T now. So I take this 0.0167. Are there any questions? I feel like there should be questions. Only because these are word problems and students have trouble with word problems. No? The 1 here, there's always a 1 in front of everything, so I just got rid of it. Log now, right? Just create your little log. Log base E of 0.0167 equals negative 0.001200968 0.001200968 T. All right, let's go ahead and do that. So the left side is a natural log, right? 0.0167. So this gives me negative 4.09234656 equals the left side, the right side. Okay. All right, so I divide that by that other number. Does anybody have it? Is anybody following along with me here? I feel so alone today. I have no one's cameras on. I'm sad. It's okay. I'll be all right. Anybody get this yet? All right, I'm flying solo. 33,829 is approximately what T is. And this is measured in years. So about 33,829 years is how old that, well, when the tree was cut down and burned, right? We're assuming it was cut down, it died when it burned. That happened about 33,000 years ago. 34,000 years. Okay,
I have a question. So the
Yes.
final product could never be negative. Is that correct?
the what?
The final product, like the final what T equals, it can't be negative, can it?
It shouldn't be. It shouldn't be.
But is it possible?
Not in a problem like this, no.
Oh, okay.
Not, yeah, I
you.
mean, because, I mean, if that happened during a test and you got a negative time, there's a problem. Because the way it's designed with the decay, it should be, you should have a positive amount of time. If you have a negative answer for time, then that means like you're going backwards in time, so you'll have like more than 100% of the carbon.
Oh,
14.
yeah. Okay, thank you.
Yeah. All right, so y'all okay with this?
Yes.
This is a big deal, okay? Because this works for anything, all right? This works for anything. So give me 30 seconds. I'm gonna come back. We're gonna do a real world problem here. I'm hoping you'll find fun. I'd like for you, since you're all at home and you're all on a computer, let's take, you know what? Let's take a minute and a half. I want everyone on their computer or whatever you got in front of you. I want you all to look up Chernobyl. Chernobyl is a nuclear reactor thing that happened in the former Soviet Union, Chernobyl. Look it up on your computer, Google it and see what you find. All right. I'm gonna ask some questions.
Was it the accident or something like that?
Yeah, it's an accident. Yeah, so tell me about it. What did you all find? Chernobyl was an accident that happened. I think there was an HBO special on this, if I'm not mistaken. It was a special recent, like within the last 5 years. What did you learn about it?
April 26, 1986.
April. Oops. It was April 26th,
1986.
1986. Okay, what happened? Where was it? In Chernobyl's, how do you spell it? CHERBYL.
NOBYL.
Okay, Chernobyl was in the former Soviet Union. What happened?
A nuclear reactor exploded.
Nuclear reactor exploded. So they basically had, they were creating electricity using nuclear fission. And that's a very complicated and delicate process that you use for that to create electricity. Well, you actually create heat from the nuclear reactions, and then from the heat you boil water, create steam, and from the steam you drive electric turbines, and that creates electricity. So you use the heat from the fission process, and it all has to be controlled. And they were running an experiment, and something happened, and it all went to shit, and it blew up, and a bunch of people died, and blah, blah, blah. Okay, so did anyone find on their research what type of nuclear material was in that explosion?
Iodine, strontium, and caesium.
What was the radioactive material though?
Plutonium.
Radioactive material, here we go. Yeah, so plutonium. I don't want to give this away, but let's see here.
It had strontium and cesium as well.
Yeah, there's cesium, right? So let me see. Most radiation release wasn't cesium. Let's just look up cesium 137 half-life. You know what? Let's go half-life. Let's just type that in. Okay, 30 years. Okay, 30 years. Let's just go with 30 years for the worst stuff that was there, okay? So 30-year half-life. Okay, can anybody find me how much of it they lost control of? This is the part that most people freak out when they hear about this. You have this huge nuclear reactor. They lost control of one of the fuel rods. How much of it did they lose control of? And how much of it?
27 kilograms of cesium.
How much?
27 kilograms of cesium.
27 kilograms. How much is that in pounds? Just so we can get a good idea of how much that is. Let's do it in pounds because most of us are more comfortable with pounds.
Around like 50.
50 pounds. That'll work. That's it. 50 pounds. You could put 50 pounds of shit into a backpack, couldn't you? I mean, put a backpack, 50 pounds in there, no problem. 50 pounds of this stuff created this catastrophic thing that went, people still can't live in Chernobyl. You can't live around it. It's what if you don't know anything about it, they lost control of it. And then they went in there and they buried it in concrete. And the guys that went in there, they're like, you know, firefighters, basically, construction guys. They went in and they backed up concrete trucks into this hole and just dumped concrete in there. And pretty much all the people who went there died within a year. You know, it's pretty crazy. But they knew that when they were doing it, they knew that it was a one-way ticket, you know, but somebody had to do it. So they encased it. All right, so let's do this. There's 50 pounds of this stuff. It has a 30-year half-life. It happened in 1986. So I want to know how much is there now. How much is still there today? All right. So this is an example of a uninhibited decay because it's a nuclear half-life. So you have our general formula. Okay. And there are a few things we actually do know here, right? Don't we know how much we started with? Right, the initial meltdown, we knew it was 50 pounds. So I'm going to put 50 pounds in here. Now we do not know what K is, do we? We don't know what K is, but we can use the half-life now to get K. How would I use this half-life? What do I do?
Left side should be 25.
So we know that when you take this formula, we started with 50, we should have half of that, right? We should have 25 there, good, equals 50 e to the k, and then t, how much time?
30.
30, right? And we're gonna measure things in years now. So this is an equation, we should be able to solve this for k. So we divide both sides by 50, we get 0.5 equals e to the 30k. And now we do our little log. We've done this already so many times today. We get that log 0.5 on our calculator again. And I'm going to go ahead and divide both sides by 30. So we get negative 0.023104 equals k, approximately. So that means now we have a final formula for the amount of this bad stuff we have at Chernobyl. There it is. That's our master formula. And now I can tell you how much is there at any point in time. And I want to know how much is there today. So this happened in 1986. So that's how many years ago?
35, I think.
About 35 years. About 35 years ago. So plug 35 in for T, right? What is the amount there after 35 years? 50 e to the negative 0.023104 times 35. And I'm gonna do that on my calculator now. I get approximately 22.27 pounds. So the half-life's 30 years. So half of it has decayed, but there's still 22.7 pounds of this stuff, which is why nobody's there. Okay, because you still have a lot of it there. And when you think of it this way, in another 30 years, half of it will be gone. You'll still have about 11 pounds there in another 30 years. Right? That's what makes radioactive materials so bad, is that it just takes a long time for it to get to a point where it's safe to be around. And this 30 years is a very, very short amount. That's a very short half-life. Okay, very short. When you look at other materials that are radioactive, like plutonium half-life, 24,000 years for plutonium. That's a long time for half of it to go away, right? So that's why this whole idea of nuclear stuff, right? These nuclear byproducts that we have, anytime you have nuclear reactors, you have this waste, this water that gets contaminated. You have to put that somewhere. You can't just like put it out in the back. You can't pour it into the ground. You have to contain it and store it somewhere. Do y'all know where they store all the nuclear waste? Do y'all know where they put it?
I think a lot of countries bury it. I'm not sure.
There's a lot of different places they put it, but they like to put them into mountains. They like to go drill big old caverns into mountains, big old tunnels, and they like to stick them into mountains. They go anywhere that they think there's not going to be an earthquake or anything like that anytime soon, and they try and put them in there. The problem is, though, that you have to get the material there. So you often have to load it onto trains and things like that, and there can be accidents. So it's a tricky business. All right, I hope that gives you some insight into radioactive decay. Let's see here. Ancient tools. Let's see, we've got about 20 minutes. Let's see if we can get through Newton's law of cooling. So this is a completely different topic, okay? Completely different topic in terms of, we're not talking about uninhibited growth and decay anymore. This is a formula that Newton came up with that gives us, like if you put, let's say you put a loaf of, you bake like a loaf of bread in the oven, right? You heat it up, or let's say you bake a cake, put it in the oven, 350 degrees, you bake it for whatever, 20 minutes, whatever it is. You pull it out of the oven, right? When you pull it out of the oven, you put it on the countertop, it's 350 degrees. But as time goes on, it starts to cool off, right? And at some point, it will reach the temperature of the room itself. Whatever, you know, if you're in your house and you have your air conditioner set at, let's say, 70 degrees, at some point, it's going to reach 70 degrees. This formula allows you to calculate how much time it takes for something to reach what's called the ambient temperature. That's the temperature of the surroundings. Does anyone know what this is used for? It's used for a lot of things, but one of the main uses for this is, when would you ever need to know how long it's taking something to reach the ambient temperature?
When you're letting food cool or something like that.
Yeah, I mean, you could, right? You could. So check this out. This is actually pretty awesome. In murder investigations, right? When they go and they find a body, let's say, you know, somebody called, hey, we found a body, right? The first thing they do when they get there is they take the temperature of the skin, and they determine, okay, what's the temperature outside? What's the temperature of the body? If the temperature of the body is 95 degrees, what can you tell me? Like, let's say outside it's, you know, 75 degrees, all right? And you find a body in the woods and you take its temperature, it's 95 degrees. What can you
It
tell me?
just died.
They've been dead not very long, right? Because humans have, you know, body temperature about 98.6. If that body is still retaining that heat and it's 95 degrees, then that happened really recently. Now, if you measure the temperature and it's maybe, you know, 82 degrees and the outside temperature is 70 degrees, now you know it's been there a little bit longer, right? The question is how much longer, right? So this equation gives you a way of calculating how long something has been there. If you know the temperature it started at, and you know the temperature of the surroundings, you can calculate how long something is going to take to decrease. Does that make sense, everyone? So murder investigations, they use this, right? Now, if you go in and you find a body, and let's say it's 70 degrees outside, and you find the body and it's 70 degrees, then this formula won't work because the body has already reached the temperature of the surroundings. And once that happens, well, then it could have been there for, a week, who knows? But there's this critical point, there's this critical timeline that we have where if you find a body and the temperature is above the surroundings, then you can use this. I hope that makes sense. So let's just read through this. The temperature U of a heated object at a given time t can be modeled by the following function. U of t equals capital T plus U naught minus T times e to the kt, where k is a negative number. Now, important things to note here. What is capital T? Capital T is the temperature of the surroundings, okay? So that's what we call our ambient temperature. That'd be the temperature of the room, okay? U sub 0 is the initial temperature of the heated object, all right? And then K is, K is basically our negative constant that helps us determine the decay or the cooling off of the material, whatever it is. All right. So let's see. Now, we're not going to do a dead body here. Okay, we're going to do whatever the book gives us. That they didn't have dead bodies in the word problem. Sorry. So we'll do what they did. Okay. So an object is heated to 100 degrees Celsius and then is allowed to cool in a room whose air temperature is 30 degrees. Okay, let me copy the formula. All right, so object is heated to 100 degrees and then it's allowed to cool to room temperature is 30 degrees Celsius. If the temperature of the object is 80 degrees Celsius after 5 minutes, when will its temperature reach 50 degrees? Okay. All right, so what is something we know from the given information? From the very beginning, is there something that we know that would help us in our formula?
U equals 100.
What's that?
U equals 100.
What U are you talking about?
U not 0. Yeah.
U not? So this is the initial temperature. Let me do it. Yeah. So just so everyone is saying it, when you have this, you can say this U sub 0, or you can say it U naught. U naught. All right, those are the two ways that you say that, U naught or U sub 0. I'm saying that because if you go on to physics or whatever it is, you're saying you want to say it right so people understand what you're talking about. So U naught here, U naught is the initial temperature of the heated object. Yes, that is 100. So U naught is 0. What else do we know? I'm sorry, U naught is 100. What else?
Constant temperature.
The constant temperature, that's the temperature of the surroundings, and that is 30, right? And these degrees Celsius, we'll just remember that. All right, do we know anything else? Just from the part that's highlighted in yellow, we know this, right? And we know this. Those are the two things we know. What we still don't know is the K, right? We don't know what K is. So let's write the formula out with what we know so far. U of T equals T, which is 30, plus U naught, which is 100, minus T, which is 30, and then e to the kt. So this equals 30 plus 70 e to the kt. That's our formula so far. We just don't know what U is. We don't know what K is. If we can find K, then we should be able to tell you anything we want. I should be able to tell you anything you want to know about this object. So the way we do it now is we use this information. If the temperature of the object is 80 degrees after 5 minutes, when will it reach 50 degrees? So 80 degrees after 5 minutes. What does that mean?
That's the left side.
The left side is the temperature of the object. That will be what?
80.
80. that happens after how much time has gone by?
5 minutes.
minutes.
5. So I replace T with 5, so 5K up there. And do you see by using that information that the temperature of the object needs to be 80 after 5 minutes has gone by? I should be able to solve for K now. And I'm just going to go through and kind of use the techniques from the homework assignment here. I'm going to subtract 30 first on both sides. That'll give me 50 equals 70 e to the 5K. I'll divide both sides by 70. So 50 over 70. Let me just get the decimal now. 50 divided by 70 is going to be 0.71428 equals e to the 5K. And then we create the log. I'm going to do the log on my calculator. And then I'm going to divide both sides by 5. So we should get negative 0.06729. I'll go to there is K. So all of that I got from that second piece of information, which allows me to now take the function and replace the K with what we know. And now we have our master formula. You give me some point in time, I can tell you the temperature of this object. You tell me the temperature of the object, and I can tell you how much time it took to get there. We have all the pieces we need. So to answer part C, determine the elapsed time before the temperature of the object reaches 35 degrees. All we would do there is replace the left side. Let me do this in a different color here. So to do this, all we're going to do is we want to know how much time it takes for the object to reach 35 degrees. So 35 is the left side equals 30 plus 70 e to the negative 0.06729 t. And then we're going to solve for t. Right? So we just follow through the same procedure. I'll let you solve that yourself. I'll leave it to you. On your homework, do number 2, do number 3, number 10, 11, and 13. I believe that's all we can do right now. Yeah. We have not done logistic models yet. We'll do that next time. So for now, just do that first page of problems. So I wanted to stop right now because I wanted to just kind of tell you again, like the way they do it, the way they do this is that if they find a body, right, what they do is they say, okay, we assume that U naught was approximately 98.6 degrees, right? That's what they assume. And then they look at the temperature of the outside. So maybe, I don't know, like I said, maybe it's 70 degrees outside, okay? So they've got 2 pieces. And then what they do is they say, okay, they go and they measure the, well, the way they can do it this way, or they can, the U naught, they can just take the temperature when they find the body. So like if they go find the body, maybe they, take the temperature, maybe the body is 88 degrees. Let's just go with that. And then what they'll do is they'll just wait a certain amount of time. Maybe they'll wait an hour. And they'll say, oh, okay, 1 hour later, the temperature of the body was 83 degrees. And then what they can do is exactly what we did here. It's like, okay, where'd it go? Yeah. So they say, oh, okay, we know the temperature of the body when we showed up, right, was 88. And then instead of 5 minutes later, it's 80, it would be an hour later, it's whatever, whatever the temperature was. And then once they have that, they can find the K. And once they have the K, then they can figure everything else out. Now, that's the way it's done, but I'm sure there's probably an app on their phones, honestly, where they just go to an app on their phone, they put in information, it calculates everything. But that's what's going on in the background, is the building up of this Newton's law of cooling function. All right. Let's wrap it up for today. Does anyone have any questions?
Sir, does it make a difference that the question says before it reaches 35 degrees Celsius?
You mean like before, are they saying, do they mean as in? I
Yeah,
think that it should be worded, determine the elapsed time when it reaches.
okay.
Yeah, I mean, that's kind of bad wording, because what would be before 35, right? I mean, what, are you talking about 34? Do you mean 34.9? I think what they really mean by that is determine the elapsed time it takes before it reaches 35 degrees Celsius, right? So they want to know how much time goes by for it to hit 35 degrees Celsius.
Okay, thank you.
Yeah. Any other questions? It would be like me, the language of that, I think, would be like this. It's like, you know, I'm expecting a delivery from FedEx today. So, you know, if I was talking to the guy on the phone and say, hey, how much time before you're here, right? What I mean by that is how much time until you're here, right? Not how much time before you're here. I think that's the confusion in the wording, right?
Yeah, that makes sense.
Okay.
For question C, would the answer just be that it experiences exponential decay?
What do you notice about the temperature as time passes? I think that all we want is really that the temperature is decreasing, right? Because it's starting out as at 100 and then it's decreasing. You could say decaying if you like. It's cooling off, right? So it's going from a higher temperature to a lower temperature. What if you find the body in the desert and it's 120 degrees outside? Then this would not be Newton's law of cooling, it would be Newton's law of heating, wouldn't it? Because the body is 98.6 degrees and then it would start to warm up, wouldn't it? Would the formula still work, do you think?
You might get a negative number for time, but theoretically.
Yeah, so what makes this thing decrease, right? This problem right here, what made it decrease was the fact that our constant that we found, K, was negative. If this thing were heating up, then our constant would be positive, but it would work the same way. So this formula would work even if it's something that's being heated. The thing is, most of the time, things are hotter than their surroundings and they cool off, which is why it's called Newton's law of cooling. But theoretically, we could use this formula in the reverse if we wanted to. If it were hotter around the object than the object actually was. Okay, keep your eyes on your email. Like I said, the plan is for me to be there Wednesday. If something changes, I'll let y'all know. Have a great day, everyone.
Thank you.
Thank
You too.
you.
Bye.
You too.
Thank you.